Hello everyone. In this video we are going to do an example on shear and moment diagram of a beam. You see a fixed support beam here. It is point load at the mid and you see a distributed load at the second half of the beam. The question asks us to draw the shear moment diagram using both equation method and graphical method. We will start with equation method. The first thing we do for the both method is to figure out the reaction forces. In order to do this, we draw a global free body diagram of the beam. We free up from the support and show the reactions. So the reaction will probably be in this direction, the vertical reaction force, and name it RAY, and the moment reaction will be this direction, that is pushing it downward, so the moment will be opposite. Call this MA. Point load 25 kilonewton. And when I find the reactions, I can write down the plot resultant of this distributed load, and it is 5 times 10, 50 kilonewton in place of the distributed load. I show the dimensions as well. Okay, now we write the equilibrium equations. By the way, I don't show horizontal reaction force here, because there is no acting horizontal force, therefore there will be no reacting horizontal force. Starting with the vertical force equilibrium equation, we have got RAY plus RAY minus 25 minus 50 equal to 0, therefore RAY is equal to 75 kilonewton. Result is positive, therefore this direction is true. We write the moment equilibrium equation at point A. We have got moment reaction MA positive. RAY has no effect on point A. 25 is rotating it negative direction. 25 times 10. 50 is also in negative direction, and 50 times 15, 10 plus 5. Is there any other force and loading that causes rotation around point A? No. When we complete the equation, MA equal to 250 here, in total 1000 kilonewton meters. Now we start doing the writing the equations for shear and moment. This is for reaction forces. First thing we do is to look at how many discontinuities there are in the beam, we see that there are three discontinuities. One is this, second is this, and the third is not this. It is here, because there is a loading here. It is about reaction forces, reaction loadings. There is a point load, and between B and C there is no change. There is a distributed load, but it is not changing. It is continuous. Therefore there is no discontinuity between B and C, and at C there is a discontinuity, which is the end of the beam and also end of the loading. Therefore we say there are three discontinuities. So first, therefore we have got two regions, three discontinuities. Within these discontinuities there are two regions, A, B and BC. Region AB, and within this region, if we choose an X term starting from the origin to the B, we can say it AX1, and it is 0, it means 0 and 10 meter. We do a cut at any arbitrary point between A and B and draw the free body diagram of the segment on the left. So we had 75 kilonewton here, 1000 kilonewton meter here. Between A and B there is no acting load, external acting load. Therefore the only thing we write, we plot, are the internal loadings V and M. Be careful that we choose positive sign convention when we show internal loadings. For V it is downward, for M it is counterclockwise direction. When it comes to drawing the shear moment diagrams, these are the positive sign conventions. I also need to show this X1. Now I can start writing equilibrium equations. Vertical force equilibrium equation. -75 minus V therefore V is equal to 75 kilonewton. I'm writing moment equilibrium equation. About a point, which point should I take? I can call this point P1. It is an arbitrary point between point A and B. So summation of the moments about point P1 is equal to 0. And what we have got here around point P1, we've got 1000 kilonewton meters minus 75 times x1. V has got no effect about point P1, and M has got an effect, so plus M equal to 0. So M is equal to 75 x1 minus 1000 kilonewton meters. Now I have determined the two equations for region AB. If we take derivative of this equation we will get this. Okay, proceeding to the region BC. Again, we draw a freebody diagram of the left hand side segment. Then we do a cut about here. For region AB we cut here, for region BC we cut here, and we use the segment on the left. Here I have got point load downward 25 kN, and also some part of distributed load. It is 5 kN per meters. And what I have got here at the arbitrary cut section, we have got shear force and moment. Again, these are the positive sign for the shear moment diagram. Here, something we need to be careful about. We don't say x1 this time, we say x2 for this distance, for the distance of this arbitrary point, and this arbitrary point is within the second region, within the next two discontinuities. These are 10 meter, 20 meters. This is x2. The distance here was 10 meters, but the distance of the arbitrary point to the origin is x2. Okay, now writing the equilibrium equations, starting with the vertical one. -75 positive, then -25, -5 for distributed load 5 times x2 minus 10, and also negative v, 75 upward, 25 downward, distributed load downward, 5 times x2, so this we multiply by this distance, which is x2 minus 10, minus v. So when we sum all of these, it is equal to 0. v is equal to 50 minus 5x2 plus 50. Therefore, v is equal to 100 minus 5x2 kilonewton. And then we write moment equilibrium equation about which point? About this point, and I call this P2. Now, what loadings causes a rotation about point P2? First one is 1000. Second one is 75, and it is in negative direction, 75. The force arm is x2. 25, the point load. It is rotating in positive direction. It is like this, about point P2. 25 times x2 minus 10, the force arm for 25, x2 minus 10, And then distributed load, it is rotating in positive direction 5 times x2 minus 10. So this is the resultant of the distributed load. We multiply this by the force arm of the resultant force, which is x2 minus 10 over 2, half of this distance. And finally, moment, internal moment, which is positive. Now we do some calculations here. 1075. Just keep using the same code. x2 25 x2 minus 250. Here half 2.5, 5 over 2, 2.5, and x2 minus 10 square. What does it give us? x2 squared minus 20 x2 100 and m 0. Now we keep doing it. Now m is equal to 100 x2 minus 2.5 x2 squared minus 1000. Is that correct? Just checking to not to make any mistake. 1000, 100 x2 m is equal to, so we take all the opposites. Okay, that's correct. Kilonewton meter. Now we have got all the equations we need in order to create the shear moment diagrams of this beam. So what were they? Where is the paper? Here. So we had two regions, region AB. For this region, and BC. For the first region, V is equal to 75 kilonewton, M is equal to 75 x1 minus 1000 meters. For region BC, we found V as 100 minus 5 x2 kilonewton, M is equal to 100 x2 2.5 x2 squared 1000 kilonewton meter. Now we can start creating the shear moment diagrams, starting with the shear. x, here v, the unit is kilonewton. For when x1 was between 0 and 10, this point 10 is point 20. Also called A, B, C. Between A and B, V is 75 kilonewton, and we know that this is the direction and it is positive for the shear diagram. I can draw this. And then looking at this equation for between BC, 100 minus 5x2 when x2 is 10, when x2 is 10, we get 50, because it is where the x2 is 10. So I go down to 50. From here to point C, I look at what I enter 20 for x2 and I get 0. So from here to here I go down to 0. So but how will it be, how will the values go down? Will it be a slope or a parabola? It will be a slope because it's a linear equation. I just couldn't catch it. Okay, let's call here 20. So this is the shear diagram using the equation method. Going next to the moment diagram. Kilonewton meter. So when x1 is 0, I look at this equation. When x1 is 0, I get minus 1000 kilonewton meter. So at the origin it is minus 1000 kilonewton meters, and I have got the other discontinuities. Upload them. At point B, see what will be the value at point B when x1 is 10. When x1 is approaching 10, the value will be minus 250. And from this point to this, there will be a slope because this is a linear equation. And in this region, between B and C, I use this equation. When x2 is 10, at this point, it is 1000 minus 250 minus 1000. So it is minus 2, it is the same point. At this point, what will be the value?